this picture is from the Mark Hadwich's lab at Stanford, showing a coherent separation of rubidium wave packets over a scale of ½ meter. And we think that by introducing these newer type of atom optics, which I'll tell you about, we can extend this by making delocalized superpositions on the scale of a few meters and then over a time of a few seconds. So this will have some implications on some fundamental decoherence models and allows us to study, like, for example, some spontaneous localization and some like nonlinear corrections to the Schrodinger equation. As I have just said, the midband actually remains an unexplored territory. On one hand, LIGO and these terrestrial-based light interferometers are limited by this vibration in the low frequencies. And the space-based detector, LISA, for example, is targeted at this like millihertz, tens of millihertz frequency, so like even lower frequencies. And historically, we know that we want to cover as many frequencies as possible, like as we learned from our observation in the EM spectrum, especially because gravitational waves offers us this entire like fundamentally new way to observe the universe. So we do not want to like miss any potential discoveries in like a certain frequency band. And it turns out that atom interferometers fill very nicely in this gap, in this midband gap. On one hand, as I've just said, atoms in free fall are pretty much immune to seismic noises. And on the other hand, the typical cycle times of these atom interferometers are just like regular AMO, many regular AMO experiments, which is like on the order of a second. Yeah, then these atom interferometers will have the potential of look at these midband sources, as I have described in the previous slide. It may be another importance for this midband is that it really is the best place to do sky localization, even with a single detector by itself. And this is because these sources just live long enough time for the detector to move with Earth like across its orbit. And then the sky localization precision is given by really this ratio between the distance between these two measurements to the wavelength of the gravitational wave we're looking at. And this midband allows a relatively small wavelength, but also like extremely long effective distance on the unit, on the order of like an AU, which means like we can use a single detector, but like measure like in various times, like in a year, and just like make fully use of the orbit of Earth to know exactly like when and where the events can happen. And then we can coordinate like subsequent observations with other detectors. So this is really this idea of multi-messenger astronomy that showed up on the previous slide. So for us, our lab is part of the matter wave atomic radiometer interferometric sensor collaboration, which we abbreviate as MAGES. And the ongoing project right now is called MAGES 100. So this is a 100-meter baseline atom interferometer currently under construction at Fermilab. So it will be located in this shaft that goes down underground for like 100 meters, which was originally built for the Nina's neutrino experiment. So here I'm showing like a cross-sectional view of the shaft. So you can see like the strong back of our vacuum system. This detector, we hope it will be an intermediate step to future kilometer scale detectors, because actually it turns out that to observe the gravitational sources, gravitational wave sources that we currently see, we would have to go for like kilometer baseline. But this will be a pathfinder for these future detectors. And we also hope that this detector can be a probe for these ultralight dark matter that I just talked about, and also serve as a test bed for quantum mechanics itself. And this picture shows the Minas lab with this semicircular shaft that goes downstairs, goes underground for 100 meters. And MAGES 100 will actually just take like this corner of the shaft, but it will use most of these steps. And on the surface, just next door, there is this empty space that we will plan to use as a laser lab. So the current status of MAGES 100 is that we have officially received this project status at Fermilab, and also we're funded through construction by DOE. So right now we are we're in the process of infrastructure engineering, and also the instrument hardware are being constructed in various institutions, including Stanford. And for the future, we plan on instrument installation at 2027, and then followed by commissioning and operation of the detector. So MAGES 100 is actually here. It's basically the first detector of a family of experiments based on the same experimental concept. So MAGES 100 itself actually will experience like different phases of operation. In its initial phase, MAGES 100 will make use of the state-of-the-art atom optics, and will also benefit from this LMT or large momentum transfer technique, which is basically saying we split up the separation of the two arms of the interferometer, but by not one, but n recoils of photons to enhance the sensitivity. And right now, for the initial stage, the target n is of around 100. So this LMT order has already been demonstrated in like lab scale interferometers. But then additional technical challenges, we'll need to address them in our strontium prototype tower at Stanford. So this tower, again, it will be a just smaller size, downsized version of MAGES 100 with full complexity. And then after its initial stage, it is expected that MAGES 100 will go on an upgrade by first of all, using better atom optics to increase the number of LMT order n. If we can benefit from the advances in laser technologies, but we'll also benefit from a higher atom flux and the possibility of actually using spin squeeze states to suppress our noise actually below the standard quantum limit. And then even beyond that, there has been studies of building like a kilometer scale version of MAGES, or also like push this experiment idea into like a space version in the medium Earth orbit. So currently, in terms of strain sensitivity, MAGES 100 in its initial phase will achieve something like 10 to the minus 14 per root hertz, given by the solid blue line. And after this upgrade, it will go down by a few more orders of magnitude. And at some point, we will suffer from this GGN, or gravitational gradient noise, whose power spectral density is shown in this orange band. So this is due to mass density fluctuating around in the surrounding environment of the detector, which causes like a local Newtonian force on the atoms. Yeah, at some point it will it will limit our strain sensitivity. In terms of future MAGES experiments, so on the right side is this plot on a like I guess like a smaller strain range. So we can see also these sources, known sources that are already observed by LIGO, and eventually, like a kilometer scale of MAGES 100 MAGES, we will be able to reach these strain sensitivities on the 10 to the minus 20 to 10 to the minus 21 per root hertz level in the midband. So over the past few years, there has been really growing international interest as well to build long baseline atom interferometers like around the world. So some of these examples include AON in the UK, which is a sister project of MAGES 100, and they share a lot of similarities. And also MIGA in France, which is a horizontal like cavity-based atom interferometer that uses this resonant cavity modes to make these atom optics. And also ZIDA in China, which is like a collection of several detectors for different science goals. So the idea is to like build out this global network of atom interferometers, just like the network of LIGO, Virgo, and CARGA of optical interferometers. So this ultimate synergy is to like make correlated observations of gravitational waves in the midband and like suppress the background and improve our sensitivity like overall compared with any individual detector on its own. So the experimental concept of MAGES is kind of similar to LIGO, that MAGES is sensitive to gravitational waves by measuring this small modulation on the baseline. So detecting this modulation will require two key ingredients. The first one is a pair of initial reference points separated at the baseline. And we require that these initial reference points must be, these are like massive objects that has to be pretty much immune from non-gravitational forces. So LIGO achieves this. LIGO actually uses these like massive mirrors at the ends of their arms as the initial reference point, and it achieves this isolation from the environment by some like very carefully engineered suspension system. For us, our initial references are like the two atom clouds separated by this baseline, like on both ends, and they are naturally decoupled from the environment because they are actually under free fall during the interferometer. The second ingredient is clocks, or like the means to measure the separation of these inertial references. And the typical way of measuring this distance is by measuring the light travel time across the baseline. So again, LIGO does this by having their light bouncing back and forth inside their arm multiple times to sample this light travel time several times. For an atom interferometer like MAGES, the atoms that actually serve as the initial references are actually playing the role of these clocks, because the light travel time is actually measured as the timing of the atomic transition. And this is encoded by the phase evolution of the atoms, which is why we say these atoms, well, they play both roles in gravitational wave detection, so they are actually like active task masses. And because of this active nature, like any phase noise in the laser is actually encoded in both atom clouds at the same time, and then they're canceled out or like rejected in a differential measurement. So this is why this experimental concept will allow a single baseline gravitational wave detector. This picture shows how we make an atom interferometer with a single photon optical transition. So here we have the atoms coming in the ground state in blue color. Then we apply a pi/2 pulse, which is we call it a beam splitter. It's like a pi/2 rotation on the Bloch sphere that separates the atom wave function into an equal superposition of the ground state in blue and the excited state in red. And then we propagate the states for time interrogation time t, and then apply a pi pulse. We call it a mirror pulse. So pi rotation on the Bloch sphere, which flips the roles of both arms. And then at time 2t, we have a second beam splitter. And in reality, we actually had more pulses in the middle to increase the momentum separation between the two arms. But then regardless of the number of pulses, in the end, we always look at the so-called interferometer phase, which shows up as a normalized population of the excited state and the ground state. So unlike Raman or Bragg interferometers, which usually uses like 2 photons, and they usually often uses alkali atoms. Here we make use of these single photon transition, which so we use alkaline earth atoms. For us, it's the choice of species is strontium. So we directly drive between 2 levels that are very long-lived with a single photon on resonance. For example, there is this 7.4 kilohertz intermediate line width transition in strontium at a wavelength of 689 nanometers. This first row in this table. It has a lifetime of 21 microseconds, which is not too long, but it turns out that we can drive it with very fast radio oscillations on the order of a few megahertz, which allows us to do like a few hundred pulses. We call this a broadband interferometer because the radio frequency is just very large, and the pulse actually is not velocity selective, and it talks to both arms of the interferometer simultaneously. In contrast, we have this narrow band atom interferometer, which uses a much narrower transition. So this clock transition, which is what enables the world's best atomic clocks, at 698 nanometers. And here, well, unfortunately, this transition only exists in the fermionic isotope, strontium-87, which is less abundant and actually harder to fool due to the hyperfine structure. But it turns out that this transition has this huge advantage that it lives for over 100 seconds flight time. So it turns out that it can support like more than 10,000 pulses, which greatly enhances our phase sensitivity. So we think that this narrow band transition will actually be the workhorse of MAGES 100 in many of its operation modes. Then we stack 2 atom interferometers on top of each other. We form this gradiometer configuration, which it is still compatible with the large momentum transfer technique I just told you about. Basically, like we can still make pulses from alternating directions to increase the separation between the 2 arms. So this shows the n=2 case. This is the lowest, like non-trivial case of this interferometer, and this n also comes into the phase, so that we get a proportional enhancement in the phase of the interferometer. And the reason for us to do gradiometry is that when the 2 clouds are addressed by a common laser, the laser noise is rejected as common mode. And the differential phase is then given by this equation, which is proportional to omega A, the level spacing, and also the baseline L, which makes this detector sensitive to certain types of dark matter candidates, which changes the level spacing, or to gravitational waves that modulate the baseline. And this proportionality to L explains why we keep pushing towards longer and longer baselines. I'm going to go through this fast for the sake of time, but basically, as I've told you, we want to use this narrowband transition, which is really good because there's not a lot of spontaneous emission, and also the off-resonance scattering rate is low. So we need to we still lose population because of the imperfections of the pulses. So here we study the effect of these imperfect pulses and how their errors add on top of each other in a interferometer sequence. And it turns out that we need to take into account of the momentum states. This is a picture of how our atom climb up this momentum ladder of block spheres. And each time we get to a new state, we actually leave some fraction of the error wave packets behind, and they follow their individual paths in this space-time diagram, creating a bunch of parasitic paths. And then it turns out that these parasitic paths do not really contribute that much as an interference background in our detection. And we are really just limited by the population loss in the main path. So I'm going to skip this on this map and not talk too much about this picture, but just to say that we apply our calculation in context to a noisy laser, and found that a moderate laser stability requirement of 10 Hertz RMS noise is actually sufficient for us to drive the 10,000 pulses that I just talked about. So before I wrap up the first part of my talk, I'm going to quickly show you a system overview of Matrix 100. So again, this is the Venus shaft cross section. So you see this 100-meter vacuum system, which is actually surrounded by magnetic shield and some structural support. To make this construction even possible, we have to cut this into smaller chunks. So these are these 5-meter modular sections with again shield and structural support, and also between these sections we have vacuum crosses for us to mount ion pumps and diagnostic cameras. And then this detector is equipped with 3 so-called atom sources that are attached from the side. So these are machines that produce optical strontium, and also with a rack for the electronics that is required. And after the generation of these cold strontium, they are actually transported horizontally into a so-called connectional chamber, which is in line with this 100-meter vacuum system. So this is a cutout of this chamber, and the red and blue things here show 2 beams that follow some complicated path, and they intersect each other in the center region of the chamber, which forms an optical lattice. So this is a periodic tracking potential, and by chirping the frequency with respect to of one beam with respect to the other, we can actually accelerate this lattice, and it will drag the atoms that are loaded in it to launch the atoms upward to initiate a fountain. This chamber is also where we do a final detection when the atoms actually fall back. And on top of the shaft, we have this laser lab that you just saw. So this is where we prepare the interferometry beam. The beam is then directed over to the top of the shaft via some free space optics, free space propagation. and then sent down into the vacuum tube. So that is the interferometry pulses. And for those pulses that travel upward, we actually have a bottom retroreflection mirror inside this chamber, which is used to redirect the light. This bottom mirror is also responsible of canceling the Coriolis effect from the rotation of the Earth by 3 piezo actuators underneath it. So let me switch gears and talk about our 10-meter prototype tower at Strontium. Again, this will be a platform to develop the techniques that will eventually be used for Mages 100, including this modular construction idea and also like the different components of the setup, like atom source, connection node, magnetic shield, and so on. So this tower, once built, we will perform state-of-the-art gradiometry on the scale of 10 meters. It will also have some unique science goals of atomic charge neutrality measurement, which will not be on the agenda of Mages 100. But I'll talk about this in the next slide. And by the way, this is the current atom source machines that we already built. We right now do not have the 10-meter vacuum system in position. So we are putting these atom source machines like side by side, but eventually one of them will be on the first floor of our lab and one of them will be on the second floor of this lab. And they will be attached sideways to the vertical vacuum system. So let me spend a little bit of time talking about QMATCH, quantum measurement of atomic charge. So the motivation is that the standard model actually does not prohibit the possibility that there's a slight like charge difference between electrons and protons. So there has been some classical null measurements in this direction, and the best bound is actually given by, I believe, some classical gas efflux measurement, which actually achieved a very good bound, like a very impressive bound of 10 to the minus 21 electron per nucleon. But here with QMATCH, we want to like break this record by making the first and best quantum mechanical measurement of atom charge neutrality. And we do this by measuring the scalar Harnack-Bohm phase that an atom interferometer can pick up when its two arms are separated by like in the region that have a big voltage or potential difference. So we make use of the Faraday cage effect, which is that like a region of high voltage can exist like deep inside a hollow a metal cylinder, but the electric field itself is vanishingly small. So if we load the interferometer such that the two arms are inside a pair of such electrodes that are separated by a high voltage, then if there's any like residual charge in the atom, it will show up as a interferometer phase that is proportional to this voltage difference. And this is exactly like the magnetic version of a Harnack-Bohm measurement, where it's like a force-free, like a field-free measurement. So we do not have to worry about the finite polarizability of the atoms. And again, we want to do this in a differential measurement in a gradiometer by putting not just one, but two pairs of electrodes. And then we can apply either a symmetric or an anti-symmetric configuration of the high voltage to cancel out like certain systematics. And we hope to get a sensitivity of better than 10 to the minus 23 electron per nucleon per shot, limited by the shot noise of the atoms.
I asked that, so the fields have to be zero inside those.
Field had to be zero.
Yeah, so it's a little bit more complicated than you're showing there in order to ensure that.
There are some complexities, like there will be some transient effects, like for example, when we charge this thing up, for example, well, the idea is we want to like actually charge them up as the atoms are already loaded inside, but then there will be some slight asymmetries, probably which will cause some finite like field, and then hopefully by doing some like as I said, like symmetric versus anti-symmetric kind of configurations, we can cancel some of that. But there is definitely like a whole like laundry list of systematics that we need to be careful about. And we have to like engineer these such that these electrodes are like really long. They're actually like about a meter long each. So like then like deep inside it, we are like the fringe field is smaller than what would be limiting us.
I don't think it's never been measured before. Has the electric effect ever been measured?
I don't think.
it has.
Yeah, well, we performed some simulations to try to verify this, and I don't think that it has been measured.
No, nobody's ever measured this before. I think it's always been too hard.
I'm
teaching this my quantum mechanics class right now. I told them it hasn't been measured yet. So
yeah. Well, yeah, I hope like it goes well, but again, like I agree that there are many subtleties that go into this. We should be careful about what we see and like the systematics that can limit us. Yeah, thanks for the comment. Yeah, I'm showing you here is the completed modular sections. They are actually lying horizontally in our lab. So these include the vacuum system and then the bake-out equipment, magnetic shield, and there's also the bellows on the far end that we need to install, which will absorb any like thermal expansion when this tube is baked at 150 degrees Celsius, and then this thermal expansion of the tube will be on the order of a centimeter. So we have to take account of that. So once they are vertical, so there will be this section on the bottom and the section on the top. They will support free fall time of like 1.5 seconds. And this is a way to for us to learn about majors, because these segments have full complexity of the majors 100 sections. So they also validate the modular construction idea. For majors, we'll actually need to build 17 of these sections. So that's a lot of work, but we're learning a lot. And we recently pumped down and baked these segments and seems to work very nicely. And here are some pictures of the assembly procedure. So the electrodes, the vacuum tube with some bake-out equipment and the magnetic shield. This is some more pictures about the QMATCH electrodes. So we have this stack of metal rings and cylinders, and also like ceramic spacers. And we like inserted it carefully into a long vacuum tube. And we've done high voltage tests under vacuum, it seemed to work well. And then we did spend lots of time engineering the magnetic shield. Because we need to suppress the ambient magnetic field down to like milligauss levels, because like imperfect quantization axis or like residual like Zeeman shifts can degrade our transfer efficiency. So we really need to have a well-controlled magnetic environment with some and then on top of it like a well-defined bias field. I have to say that we are fortunate that to work with strontium atoms, because it's an alkaline earth atom. It has 2 valence electrons, so the ground state and the clock state both have J equals 0. So it's not nearly as sensitive to magnetic field as alkali atoms. The fermionic isotope does have a nuclear spin, but then again, the susceptibility is like suppressed a lot by the ratio between nucleus magneton and Bohr magneton, so like 1/1000 ish. But still, we need to build a good magnetic shield. it's just like we do not have to like build a multi-layer shield as we would in the case of the ultralight interferometer. So we build a single layer shield by actually stacking multiple sheets of mu metal together in a way that the gaps are we call staggered, it's like misaligned, such that the penetration of the Earth field is minimized. And then in the longitudinal direction, we also have to do similar kind of staggering in the same spirit, just because that our section is just too long. It's longer than any annealing furnace of mu metal. So we need to really need to stack multiple mu metal pieces in the longitudinal direction, which is indicated by this color code. And then all the mu metal pieces are just clamped together by these pressure plates and then into an octagonal periodic backbone on some 80-20 structure. So that's a lot of work. It actually requires us to fasten 800 screws with the same torque all around. But once this is done, we have a beautiful magnetic shield, and we could measure the magnetic field along this axis. We did this by running a magnetometer and a data logger along the axis. We did this very carefully by using some suspension cable car system, so that the equipments will not touch the vacuum surface, and we get something like this. So we still have some anomalies, which I think comes from either impurities or cold work from our 316 stainless tube, but the overall RMS background is below 1 milligauss, so it is already within our spec. And then on top of that, we added these bias bars, which are conductors in black. I don't know if you can see it. These conductors that run along the direction of the tube. And we arrange them such that they create a uniform magnetic field in the horizontal direction. We had to do some finite element study just to see how they interact with the magnetic shield, and just make sure that they actually produce a Helmholtz-like field with good homogeneity around the center of this tube. And here is the atom source. So we have a fully functional two-stage malt. And right now we're working towards adding an optical dipole trap for matter wave lensing or possibly evaporation. And also some lattice shuttling to move the atoms from this chamber to the interferometry region. And also there's ongoing work to develop future atom sources for majors, which would again require this whole setup to be self-sustained with this racks for electronics and laser. And it means a better enclosure for environmental control under the shaft, and of course with some remote adjustability for this thing to be self-sustainable in the shaft. While we're doing all this building, we're also using the cooling chambers in our atom source as science chambers to do some small-scale interferometry measurements. So for the past few years, we have been interested in this broadband interferometry idea, which is using this the intercombination line, this 7.4 kilohertz transition, to do very fast atom optics that addresses both arms simultaneously. We have demonstrated an interferometer with this large momentum transfer technique. And we also found ways to amplitude modulate our pulses such that even when these two arms are separated by hundreds of photon recoil, we're still efficiently talking to both arms simultaneously. So I guess for the as the last part of the talk, I'll talk about some optical lattice ideas, which we use to move the atoms around and also launch the atoms to form a fountain. The shuttle lattice we require the shuttle lattice to move the atoms from our Mach chamber into the connectional chamber, which is separated by an overall distance of like 60 centimeters. So the idea, the way for us to do this is actually to move the atoms with two lattices. So one lattice, those lattices are like tilted by a small angle, and then the basic idea is to like launch and like toss the atoms at some velocity, but with some vertical velocity component, which will counteract gravity. Because otherwise, for this time scale of transport of like around 50 milliseconds, the atoms will sag under gravity for like a centimeter or so, which is not great. So we need to like have some angle in the lattice and do a toss and catch. So the atoms actually follow a parabolic trajectory from the first lattice into the second lattice. And the second lattice will be velocity matched to the kinematics of the atoms and then stop it at the center of the second chamber. So we went on and designed some optical layouts that achieve this. So basically we have two inputs from fibers with noise cancellation. And then they are aligned on top of each other on the round trip, which gives us like two usable lattice regions. We also put these lenses at proper locations to such that actually the conjugate points of the optical system make sure that the angle of this cross is decoupled from the position of these lattices. So then it allows us to diagonalize our system in terms of alignment. For this lattice light, we plan to use actually a blue detuned light from our from the 689 nanometer transition in order to suppress spontaneous emission loss. And here is the delivery setup for the lattice. So we try to compactify our setup, partially because we are constrained by space in our setup, but more importantly, because we want this good stability, like long-term stability for mages, especially when it's like under a shaft. So these red objects that you see are picomotors, and we have position sensors that will allow us to remotely tweak this. So we're really trying to incorporate all the functionalities for Magus 100 of like remote actuation. And once again, these knobs are arranged in such a way that can diagonalize or like orthogonalize the adjustment of the angle and the position of the lattice. So finally, the launch lattice, we would need something like over 100 G acceleration in the vertical direction, and this is achieved by a vertical lattice in this like diamond region by sending in two beams, and they are expanded and redirected at steep angles to form this overlap of around 8 centimeters. Again, we try to use the same trick to diagonalize the degrees of freedom, and it's also a blue detuned lattice. And if I zoom in, you can see this nice diamond-shaped region, which is where the atoms will be loaded and then accelerated upwards. And finally, I'm going to show you this lattice delivery picture. So this module that's outside vacuum, and we also put these in-vacuum optics attached to this chamber, and also I don't know if you can see it, but there's some supporting structure that holds the mirror like on top of the chamber and also on the bottom of the chamber. So we have demonstrated this independent angle and position adjustment. And also we bake the system and make sure that everything is still aligned after the bake. So those lattices hopefully will test them on real items once our system is fully built. I hope this will be in the very near future. We're like talking about we have recently like upgraded our crane and talking about making the sections vertical like by the end of the year. So that'll be really exciting. And then finally, as a summary, Matrix 100 will be this next generation 100 meter baseline atom interferometer, which is still under construction at Fermilab, and will play the role of like a pathfinder for future kilometer scale gravitational wave detectors. It will also serve as a probe for ultralight dark matter, and also a test bed for large scale quantum mechanics tests. And then as a prototype and to build this platform to demonstrate techniques that we transfer to Matrix, we are kind of sprinting towards the finish line to set up this 10-meter gradiometer at Stanford. And by itself, this will also be a state-of-the-art machine to do gravity gradiometry on a scale of like a few meters. And it also has these unique science goals of like atom charge neutrality measurement. This is a mature detector design, and everything is like most of the system is actually already put together, and we are kind of looking forward to the final assembly, which will happen like in the very near future. So I guess that is the end of this talk. I would like to acknowledge my great team and my PI, Jason, and also this is a list of our great collaborators of Matrix 100. With that, I'd like to thanks for your attention, and happy to take any questions.
Yeah, so pardon my ignorance, but this is the first time I've heard of gradiometry. So I don't think I understood how exactly y'all read out your data and what you expect your signal to look like.
I see. That's a good question. Do I don't really have a gradiometer slide. But let me go back to this slide where I talk about the gradiometer itself. Oh, yeah. Oh, new share. There we go. Oh, sorry, it's not there. Yeah, I think that is will work. I think I can just, or I can duplicate. I think I'll do duplicate. Sorry. So yeah, a gradiometer works by stacking two interferometers on top of each other. And the reason, there we go. Yeah. Does the screen share look good? Yeah. Yeah. Thank you. So each interferometer in the end will contain like we'll count the population in a ground state and the excited state, and then we extract the phase by like the ratio between them basically. But if you only do one interferometer, you'll notice that your laser noise is actually imprinted as part of this phase. So you see that in different shots, this phase actually like moves around. By doing a gradiometer, we measure both the phase of the upper interferometer and then the phase of the lower interferometer. And then when we subtract the two phases, we can see that so that the laser noise is basically like canceled, and this differential phase will be stable. So this is the basic idea of gradiometer. And then it turns out that we can actually scan the phase of the upper interferometer with respect to the lower interferometer. So we can introduce like an artificial phase Or like a gravitational wave, for example, can like put a differential phase between the two interferometers, and then you will see the upper interferometer will have a different phase compared with the lower interferometer, and that allows you, that is the signal that we're trying to measure. That answers the question. Yeah. Yes.
Yeah, I had a question about the large momentum transfer scheme. So just to make sure that I'm understanding right, the idea is like you sort of like you prepare your superposition and you like high pulse, and like the atoms sort of like do like this, and then you let the interferometer in place.
Yes.
Is there, and forgive me, so I'm coming from the world of Bragg interferometers, like not super used to the idea of using the clock conditions today. But is there an advantage to using this over like a Bloch oscillation or something like that?
Oh yeah, that's a good question. So well, I guess one reason that we do clock interferometry, which uses a single photon instead of using like a 2-photon transition, for example, is that it actually turns out that for in the 2-photon transition, you need to take into account of like the timing of both pulses onto your atom, and that makes the common mode rejection of the laser noise not as good as what you have with a single photon, because here like when a single pulse comes and talks about both atoms, the laser noise is just imprinted onto both clouds. But if you have 2 photons, then the two pulses will never like talk to both clouds simultaneously. Like you always like talk to the top first, and then you actually need a second pulse from the bottom in order to talk to the bottom cloud, or vice versa. So this is one reason to do it this way. Then another important reason for us to prefer clock atom interferometer in this like long baseline measurement is that the lifetime of the excited state is really long. In case it's strontium, it's like over 100 seconds. So if you want to do like 2-photon or like multi-photon interferometry, you need to like be really like detuned from the virtual state in order for you to suppress spontaneous emission. Which means you need to, if you want to keep up your Rabi frequency, you need more laser power. But you cannot play this game like forever, because laser power is at some point will be limited. But we think that for clock atom interferometry, like this 100-second long lifetime is basically infinite for us. So like we can always like as long as we can fit in these pulses within the free fall time, can always do more. Yeah.
No, there are no questions. Thanks.
I have one.
Yeah.
Yeah, you had the restrictions on the magnetic field shielding. What about electric fields?
Yeah.
In the background, you have metals around patch potentials.
Yeah, that is a great question. Yeah, I don't really have a good answer to that, unfortunately. I guess it depends on the polarizability of the atoms. Yeah, I have to say I did not think very much about this. Let's see.
I don't think so now. I just wondered if you have, because
no,
does that fail because of background field?
Right. I
think that you're probably okay, but
I think we're probably okay. I guess one thing it is also like it's only the electric field, I guess, in this frequency band that we're looking at stuff that will affect us.
that's likely because this is a stochastic process, and I'll drive decoherence, I think.
I guess you're right. But no, unfortunately, I don't really have a good question, good answer. Sorry. Yeah, this is a great question.
I have one more question, sorry. So the aspect ratio of the chamber for the Magus 100 experiment is going to be really quite large, a small whichever page.
Yeah.
My question is like, how big are you going to make the interferometry beam so that the light range is like long compared to the chamber? And what does that mean about the constraints on the size of the diameter of your chamber?
That's a great question. So the size of this beam, you're right that we need to be careful about the beam cannot be too small, because first of all, as you said, if you make the beam too small, then the radial range will be short, and we'll experience either like diffraction from the pipe, or the two clouds or three clouds at different positions will see different intensity. And on the other hand, there's another reason for us to not like a small beam is because the intensity profile across the beam will roll off. And if that scale is comparable to the size of the atom cloud, then we're in trouble because then the atom cloud will not see a uniform Rabi frequency, and that leads to some that will explain out our phase. So for us, we are actually really like trying to get as much as big of a beam as possible, while still maintaining a reasonable Rabi frequency. As I said, like kilohertz level for the 698 transition. And this means a beam size of on the order of like centimeter or more, like few centimeters. And to achieve this, we need to have our vacuum system being like even larger. So we're actually using a 6-inch ID tube. And so we think that this amount of aperture like is okay in terms of diffraction. And then the radial range of this beam is basically like much longer than our experiment. But still, you might be concerned about like some light being diffracted and like bounces around the system. So there has been these ideas of putting like baffles along the length of the detector to like absorb these light, so that they don't like come back and affect the interferometer. That's a great question.
You sent out my suggestion. I worked on an experiment that goes to 5 meters out in Berkeley, and we had this exact problem where we were trying to make the beam very large to have the Rabi frequency be formed with the size of the atom cloud, and that meant that we needed to. We also were very concerned about speckle from like stray light, bouncing up and down the tube. And we installed baffles, and this helped tremendously. And ended up meaning that the inside of our vacuum chamber needed to be really quite large. We used an 18-inch diameter.
An 18. Wow.
And so our beam size is about the same as about an inch.
See. Yeah, we also hope that with some like composite pulse techniques, we can maybe like improve this by being able to use like smaller size beams, and cancel out like the inhomogeneity effects to at least the lowest orders. We're still in the process of like studying this, seeing how much composite pulse can help.